Hey guys, how are you doing today? My name is Milushianev. Will and I will be presenting chapter 30 in our textbook regarding a categorization of real-time multiprocessor scheduling problems and algorithms. I want to apologize that my camera is not here, but I'm recording this on my PC, so it doesn't come with a camera. First, let's talk about our brief overview and how this presentation will be presented. I will cover the introduction, classification of scheduling approaches on multiprocessors, taxonomy of scheduling algorithms, and we'll continue with the schedulability relationships, algorithm design and feasibility analysis, and partition approaches. We also have some examples for you from the book and some examples regarding some extra content that we found online as well. Unlike several years ago, real-time multiprocessor systems are now more commonplace. Most designs consist of system built with a single chip architecture with a modest number of processors. However, when it comes to companies, we see that moving from such systems to large-scale signal processing systems, such as synthetic aperture radar systems. The problem of uniprocessor systems is ensuring that deadline constraints are met. Researchers are in the very beginning of understanding the trade-offs that exist in multiprocessor systems. The purpose of this presentation is to analyze the trade-offs involved in scheduling independent periodic time tasks on a multiprocessors. According to our book, real-time scheduling has largely focused on the problem of scheduling of recurring processes or tasks. In the model of Liu and Leyland, a task T is characterized by two parameters, a worst-case execution requirement E and a period P. This particular task is invoked at each non-negative integer multiple of P. Each invocation requires at most E units of processor time and must complete its execution within P time of units. A collection of periodic tasks is referred to a period task system, and it's denoted by T. As you can see here, there is a simple example of the algorithm regarding a real-time systems schedule, which is schedulable under the RM. If you see the formula UI is less than n, and etc. We're going to discuss that thing later on. I just pulled this one out of the Journal of the ACM of 1973 regarding the Liu and Leyland scheduling algorithm examples. Okay, as said before, let's talk about some of the interesting stuff. Traditionally, there have been two approaches for scheduling periodic tasks on multiprocessors. We have the global and the partitioning schedule. In order for global scheduling to be executed, all tasks must be stored in a single priority order queue, and the schedule takes one by one in the highest order available. There is a downside of using this method though. Although such as the rate monotonic RM, the one that I showed you before, or the earliest deadline first algorithm, or the EDF, they may result in arbitrary low processor utilization in multiprocessor systems. We're going to go over another example, and that's going to be for the least laxity first, or the LLF scheduling algorithm. First rule of business is the question, what is RM scheduling? Well, the rate monotonic scheduling algorithm is a simple rule that assigns priorities to different tasks according to their time period. That is, a task with the shortest time period will have the highest priority, and a task with the longest time period will have the lowest priority for execution. It works on the principle of preemption. This process occurs on a given processor when the higher priority tasks task blocks a lower one from execution. This occurs due to the original setup where the high is always going to execute before the low. And RM priorities are assigned according to the time period. Task with the lowest priority time has priority, higher priority, and vice versa. The equation used to satisfy the condition is actually explained on the previous. It is explained over here, if you can see my mouse. And the equation states that C over T stands for the execution time over period, and N is actually the number of tasks in the task set. Next step is to go over a simple example and explain how the algorithm works. As you can see here, we have three tasks with respective values. When you plug in the numbers as shown for U in the middle, we'll get 0.75. If we have to break down this example, it will happen in actually 7 steps, and due to the importance of it for this presentation, I will have to go over them. First step is going to be a task with shorter period of time has priority, so T1 has higher priority, and T2 has intermediate priority, and T3 respectively has the lowest priority. At time 0, all tasks are released. Now T1 has the highest priority, so it executes first until time is equal to 0.5. At time equal to 0.5, task T2 has higher priority than T3, so it executes first for one time until time is equal to 1.5. After its completion, only one task is actually remain in the system, and that's going to be T3. So it starts its execution until it hits time equal to 3. At time equal 3, T1 releases because it has higher priority than T3, so it preempts or blocks T3 and starts its execution until time hits 3.5. After that, the remaining part of T3 executes. At T4, or time 4, apologies, at time 4 actually, T2 releases and completes its execution as there is no running tasks in the system at this time. At time 6, both T1 and T3 are released at the same time, but T1 has higher priority due to the shorter period, so it preempts T3 and it executes until time is actually hitting 6.5, and after that T3 is going to start running and it's going to execute until time is equal to 8. At time equal 8, T2 with higher priority than T3, it's actually going to release. So it preempts T3 and it's going to start its execution. And then lastly, at time 9, T1 will release again, and it's going to preempt T3 again, and it's going to execute first at time is equal to 9.5, and then T3 is going to execute the remaining parts. And similarly, we can go on and use the same logic 2 more times. I'll drink some water real quick. Alrighty, so next we have to go over the earliest deadline first scheduling algorithm. So what is it? Well, the earliest deadlines first scheduling algorithm, or EDF, is a dynamic priority scheduling algorithm for real-time embedded systems. The main goal behind this is the selection of a task according to its deadline, such that a task with earliest deadline has higher priority and vice versa. Due to the dependencies on the current instant of time, every instant is actually a scheduling event as a deadline of tasks is going to change with time respectively. Because of this, a task with higher priority due to the earliest deadline at one instant may have actually lower priority at the next instant due to the early deadline of another task. Same as the RM, EDF typically executes in preemptive mode. The formula used for EDF can be seen in figure 2, where CI is the worst case computation times of end processes and TI is its respectively inter-arrival period. In case of a non-preemptive uniprocessor calculations, EDF is an optimal scheduling algorithm, but only among the class of scheduling algorithms that do not allow the inserted time. The formulas for such instance can be seen in Figure 3, where P represents the penalty for non-preemption. Now let's go over an example again. If you plug in the numbers here and using the first formula, which is going to be this one, if we use the first formula from Figure 2, we'll actually get 95% of utilization. In order to break down this example, we'll have to actually execute this one in 6 steps compared to 7 steps in the previous example. At T1 or time 1, all the tasks are released, but priorities are decided according to their absolute deadlines. So T1 has higher priority as its deadline is 4, earlier than T2, whose deadline is 6, and T3, whose deadline is 8, and that's why it executes first. At time 1, again, the absolute deadline are compared, and T1 has shorter deadline, so it executes, and after T3 starts its execution, but a T4, T1 comes in the system and the deadline are compared, and at this instance, actually both T1 and T3 have the same deadline, so ties are broken randomly, and we'll pick just T3 to execute. At time T6, T2 is actually released, and now the deadline of T1 is earliest or earlier than T2, so it's going to start executing after T2 begins to execute. At time 8, again T1 and T2, they have the same deadline, and then we're going to go to time equal to 16, so the ties are broken randomly, and T2 continues to execute, and then T1 completes. Now time 12, T1 and T2, they come in the system simultaneously by comparing the absolute deadlines. T1 and T2, they have the same deadlines as before, and we're actually going to break it down randomly, and we're going to continue with T3 again. At t equal 13, T1 begins to execute, and it's actually going to end at t equal 4 or time equal 14. And now we have T2, which is the only task in the system, so it completes the execution. At time 16, T1 and T2 are released together. Priorities are decided according to the absolute deadlines, so T1 executes first, as its deadline is equal to time equal 20 and T3 deadline is equal to time equal 24. After T1 completion, T3 starts and reaches time 17, where T2 comes in the system. Now by deadline comparison, both have deadline of time equal 24, so ties are broken. And then we have T3 continues to actually execute T3. Wait, no. We actually have to execute T3. Time 20, both T1 and T2 are in the system and both have the same deadline at time 24. So again, ties are broken randomly and T2 executes. After that, we have T1 that's going to complete the execution, and in the same way, we're going to continue to run without any problem following the EDF algorithm. I apologize for the confusion, but if you follow the math, I'm hoping I did it right, but it should be right, and the numbers should match if you watch the presentation again, which probably won't happen. So third and last, we have to go over the least laxity first algorithm. And just want to give you a quick heads up. For some reason, I forgot to put in the figures, but I'm going to refer to this one. Let's see, as figure 4, and then this one is going to be figure 5, since we already did 2 and 3. So this is going to be figure 4, and this is going to be figure 5. What is least laxity first algorithm? Well, LLF actually consists of job level dynamic priority scheduling. Every instant is a scheduling event because of the laxity of each task changes on every instant of time. A task with higher priority must have least laxity at an instant. Priority of a task is inversely proportional to its runtime. And then in figure 4, we'll observe the formula where the laxity of a task is defined as its urgency to execute. Here DI is going to represent the deadline of a task, and CI is the worst case execution, and the LI is going to be the laxity of a task, which means that the laxity is in the time remaining after completing the WCET before the deadline arrives. Another way of calculating the laxity is actually shown in figure 5, where you can see that the current instant of time and the remaining time of a task. By the equation of figure 5, the laxity of each task is calculated at every instant of time, then the priority is assigned. One important thing to note is actually the laxity of running task does not change. It remains the same, whereas the laxity of all other tasks are decreased one by one after 1 unit of time. But now, actually, let's dig into the first example and then the second one. So if you see here, we're going to have several different approaches over here. So first, at time 1, so I'm going to refer to this one as time, and then we have T1, which is going to be the task 1. So at time 1, the laxities of each task are calculated by using the equation as, let's go back, L, as L1 is equal to 6 minus 0 plus 2, or that's going to be equal to 4, and then we have L2 is going to be equal to 8 minus 0 plus 2, which is going to be equal to 6. And we have L3, which is going to be 10 minus 0 plus 3, which is going to be 7. As task T1 has least laxity, so it's going to execute with higher priority. Similarly, at time 1, its priority is calculated, and it's actually going to be 4, and then T2 has a time of 5, and then T3 has a time of 6. So again, due to the least laxity, T1 continues to execute. Next, at time 2, T1 is out of the system, so now we have to compare the laxities of T2 and T3 as follows. L2 is going to be equal to 8 minus 2 plus 2, or that's going to be 4, and L3 is going to be equal to 10 minus 2 plus 3, or that's going to be equal to 5. Clearly, T2 starts executing due to the least laxity in T3, and at time 3, T2 has a laxity of 4, and then T3 has also actually a laxity of 4. So ties are broken randomly, and we continue to execute T2. At time 4, no task is remained in the system except T3, so it's going to execute until time hits 6. And then at time 6, T1 is going to continue in the system, so laxities are calculated again as follows. L1 is going to be equal to 6 minus 0 plus 2, or that's going to be equal to 4, and L3 is going to be equal to 10 minus 6 plus 1, or that's going to be equal to 3. So T3 continues its execution. At time T8, T2 comes in the system, whereas T1 is running the task. So at this instance, the laxities are calculated as L1 is going to be equal to 12 minus 8 plus 1, that's going to be equal to 3, and L2 is going to be equal to 16 minus 8 plus 2, which is going to be equal to 6. So T1 completes its execution. After T2 starts running at a time equal to 10, due to the laxity comparison, T2 has higher priority than T3. So it's going to complete the execution as follows. L2 is going to be equal to 16 minus 10 plus 1, which is going to be equal to 5. And L3 is going to be equal to 20 minus 10 plus 3. That's going to be equal to 7. Where time is equal to 11 and only T3 is in the system, so it starts the execution, and vice versa. You follow the logic. From now on, we have 2 more steps, but I'm not going to go over them because it's getting boring, to be honest with you, for probably for you. So let's go to another example. Um, least laxity first scheduling algorithm. I'm going to go into very details on this one because it's going to be too boring, and I have to go over the math again, which is going to be consisting of probably, not probably, but I think it's 9 steps to be exact from what I see. So we're just going to talk a little bit about it. The algorithm is good for avoiding transient overload and domino effect occurring in the EDF. But it also actually has a shortcoming that's going to be trashing. When more than one task hits these axity, this phenomenon of trashing actually occurs. Trashing is the behavior of preemption by the task one at each time. This kind of preemption results in context switched at each instance of time. This context switching results in more computational power consumption as switching from one task to another will result in saving and loading registers, memory mapping, and uploading many tables and lists. So it results in loss of computational time as well. To overcome this shortcome of the LOF, an improved version of LOF is introduced, and that's going to be called the Enhanced Least Laxity First Algorithm scheduling algorithm, which is going to be ELLF. In ELLF, whenever more than one task has least laxity, then they all are grouped together, and the EDF is applied within the group, whereas taking this group as a single task, LOF is applied to the group as well, and the remaining tasks um, are set up again and again and again. As an example of an ELF with trashing is given on this slide, as you can see with the arrows. So in order to overcome this context switching due to trashing, we employ the ELF in the same example by grouping together the tasks of having least laxity, then applying the EDF to avoid context switching. So, one second. So as you can see on the example, pretty much how it works is we're going to execute the LOF at once, and then we're going to group that with the other group, and etc. And that's going to be turned into, eventually the ELLF. So over here, so one becomes two, and then three, and etc. and etc. and etc. Next step, we have to go over the classifications of scheduling approaches on the multiprocessors. First, we have to talk about a little bit of partition scheduling. Partitioning is, in the other hand, is going to actually use the opposite approach of the global one, where each task is assigned to a single processor on which each of its jobs will execute, and processors are scheduled independently. The main advantage of this method is the reduction of multiprocessor scheduling problems into a set of uniprocessor ones. The downside of using this approach is that finding an optimal assignment of a task processor is a bin packing problem, which is actually an NP hard one. Another drawback, in order to for a task system to actually exist and to be schedulable, the task must not be partitioned. In addition to the top two approaches, there is a new model that we're talking in the book, and then as well as we found some information online, or that's going to be the so-called middle approach. It's going to be a combination of the two approaches that we already described, where each job is assigned to a single processor while a task is allowed to migrate. And we believe that migration is I'm sorry about that. We're talking about, yeah. So we believe that the migration is skewed in the design of multiprocessor real-time systems because if its true cost and thermal of the final system is going to be actually produced not as well. So as a step towards understanding this cost, we have to present taxonomy that ranks scheduling schemes along the follow two dimensions. I just got lost because I had to quote one of the quotes in our book, and I guess I lost the quote for a second. First, the complexity of the priority scheme, where scheduling disciplines are categorized accordingly to whether the task priorities are first static, second dynamic, but with fixed within jobs, or third fully dynamic. Common examples are going to be the RM, explained in the previous chapter, EDF, explained in the previous chapter as well, and the LOF, scheduling. The second dimension is the degree of migration allowed, where the disciplines are ranked as follows. First, there is no migration. Second, where migrations are allowed, but only at job boundaries. And third, when we have unrestricted migrations. Okay, so consider the fact that the scheduling algorithms execute each task individually. It is very important for them to be simple and efficient. The operation flow of most scheduling algorithms is actually work conserving. As previously mentioned, in the highest priority jobs, we actually will always execute first because we have high to low execution. And in such algorithms, the process is never left idle while an active job exists. The only execution to the logic explained above is, let's say, when a migration constraints prevent the task from executing, where that specific process is stuck on idle. And I'm just going to use a quick quote from the book. Because of the runtime overheads of such algorithms tend to be less than those of non-working conservative algorithms, scheduling algorithms that make scheduling decisions online tend to be work conserving. What does that mean? Well, it means that the effectiveness of the scheduling algorithms depends on not only its runtime overhead, but also its abilities to schedule feasible tasks. There are two reasons behind inter-processor migration being forbidden in real-time systems. One of them is that in many systems, the cost associated with each migration can be prohibited, and the second one is that traditional real-time scheduling theories lacks the techniques, tools, and results to permit detailed analysis of systems that allows migrations. Um, Therefore, partitioning has been the preferred approach of migrations in the scheduling algorithms. According to our chapter 30 in Long and Anderson's book for scheduling algorithms, the results of experiment conducted demonstrate that the scheduling algorithms that allow migrations are competitive in terms of schedulability with those who do not migrate even after incorporating the overhead, because we always have to incorporate for the overhead. As previously described in order to differentiate among the multiprocessor scheduling algorithms and their degree of migrations, we're going to actually use three categories. Category number one will be when there's no migration, and then category number two is going to be mid-migration, and then we have category number three, or I mean, category number two is going to be the restricted migrations, and then we have category number three, it's going to be the full migration. So if we have to go over it briefly, we can just say that, actually we can just move on to the full migration where no restrictions are applied. And let's run this example. This is the exact example from our textbook. And as you can see here, the scheduling algorithm is X and Y. It's going to restrict it for X that belongs to 1, 2, 3, and Y that belongs to 1, 2, and 3 as well. And if it's in priority class X and migration class Y, here X and Y corresponds to the labels defined above. For the example, let's say 2.1, restricted algorithms uses a job level dynamic priorities. And then we're going to hit partitioning, And while 1 and 3, which is going to be the restricted algorithms that only use the static priorities, which is going to be level 1 priorities, this is going to allow unrestricted migration. And then we have 9 categories of scheduling algorithms because of the table 3 by 3. And it's natural to associate all the classes of scheduling algorithms with the set of tasks that they can schedule. So let's talk about taxonomy of the scheduling algorithms. As previously described above, for priority-based classifications, in order to differentiate among the scheduling algorithms according to the complexity of priority scheme, um, there are 3 categories that we have to consider as well. First, we have the static priority, where a unique priority is associated with each task, and all jobs are generalized by the task priority as well. Thus, if in task T1 or task 1, let's say have a higher priority than task 2, then whenever both have active jobs, T1 job will always have priority over T2 jobs. And we actually saw that in the RM example, and it's in the part of the EDF as well. Second is going to be the job level dynamic priority, where for each pair of jobs, let's say job I and job F, if job I or JI um, has a higher priority than JF, at some instances JI will keep higher priority until execution is done. And we can actually refer to this example as the EDF scheduling. That's why I said it's important to go over them briefly in order for us to continue with this presentation. And then, as you probably already figured, third is going to be the unrestricted dynamic priority, when we will have no restrictions. And a good example is going to be the LOF scheduling algorithm. By actual definition, dynamic priority algorithms are actually generalized of job level dynamic priority, and they are turned into a generalization of static priority algorithms. In uniprocessing scheduling, the distinction between job level and unrestricted dynamic priority algorithms is actually rarely emphasized. Because as discussed above, the EDF scheduling algorithm can provide an optimal solution. Despite this, in multiprocessor case, unrestricted dynamic priority algorithms are more powerful than the EDFs. In order to prove the above 2 statements, a mathematical matrix model, same as the one before, can be used, but a little bit different. For calculations to be done, an example using the X, which is going to be the priority assignment constraint, and Y, which is going to be the migration constraints, access matrix can be plotted to prove the concept. And as you can see, it's going to be 3 by 3 class of scheduling, same as the one before. And let's go over this example real quick. An order pair denoted by X and Y denotes a set of tasks that are feasible under X and Y restricted scheduling. As we said before, X is going to be priority assigned constraint, and Y is going to be the migration constraints. Of these 9 classes, say 1 and 1, 2 and 1, and 3 and 3, they're going to be restricted algorithms that have received most attention. For example, 1 and 1 restricted algorithms have been studied in 3, 12, and 14, while 2 and 1 restricted algorithms have been studied in chapter 3, 15, and actually 16. I'm mentioning that just in case somebody wants to go over them. The examples are pretty cool once you actually go over the chapters and realize what exactly are they talking about. The class, let's say, of 3, 3 in this case, is going to be restricted algorithms, and we can see them in 1, 4, 6, and 8. In addition to these, we have 1 and 3 and 2 and 3, which is going to be restricted algorithms as well, and they're considered in the same chapter, respectively. So as you can see here, we have a breakdown of partition, restricted migrations, and full migrations, but we actually have it from bottom to top. And we have the jobs as static, we have dynamic, and unrestricted dynamic. It's a pretty cool example once you plug in the numbers. There's a couple of them in the book, but we have to spend at least 10 more minutes to go over them, and unfortunately, we don't have that time. And now we'll actually continue from here on, and we'll start talking about the schedulability relationships. Thank you.
Thank you, Milush. We now consider the problem of establishing relationships among the various classes of scheduling algorithms in the last table. Our goal is to study the trade-offs involved in using a particular class of scheduling algorithms. It is generally true that the runtime overhead is higher for more general models than for less general ones. The runtime overhead of a WNX restricted algorithm is at most that of a Y and Z restricted algorithm if Y greater and equal than W and Z greater and equal than X. However, in terms of schedulability, the relationships are not as straightforward. There are three possible relationships between W and X and Y and Z restricted scheduling classes. It is often the case that we discover some partial understanding of a relationship in one of the following two forms. W and X belongs to Y and Z, and W and X not belong to Y and Z. It means any task system in W and X is also in Y and Z, and there exists a task system that is in W and X but not in Y and Z. For the notation one, the class of W and X restricted algorithms and the class of Y and Z restricted algorithms are equivalent. That is, a task system is feasible under the W and X restricted class if and only if is feasible under the Y and Z restricted class. For notation two, the class of W and X restricted algorithms and the class of Y and Z restricted algorithms are incomparable. That is, there exists at least one task system that is feasible under the W and X restricted class, but not under the Y and Z restricted class, and vice versa. For the last notation three, the class of W and X restricted algorithm is strictly more powerful than the class of Y and Z restricted algorithms. That is, any task system that is feasible under the Y and Z restricted class is also feasible under the W and X restricted class. Furthermore, there exists at least one task system that is feasible under the W and X restricted class, but not under the Y and Z restricted class. Below is a list of task systems that will be used to further separate the algorithm classes. Each task is written as an ordered pair E and P, where E is the execution requirement and P is the period. The number of available processors is denoted by M. In three of the following lemmas, we make implicit use of theorem 30.1 to establish certain results. Now for lemma 30.1, consider the 1 and 2 restricted algorithm. T2 has higher priority than T1, which has higher priority than T3. Restricted migration is permitted. For example, each job must execute on only one processor, but different jobs may execute among different processors. The resulting schedule, based on the figure 30.1, shows that A belongs to 1 and 2. Only the schedule in closed 0 and open 6 is shown, since 6 is the least common multiple of all the task periods, and the schedule starts repeating after time 6. The lemma 30.2, A is not belong to 1 and 1, and A not belong to 2 and 1, and A not belong to 3 and 1. The proof of this lemma is the tasks cannot be divided into two sets so that each set has utilization at most one. As we can see from the figure, a 3 and 3 restricted schedule for task system B. Figure 30.2 shows the 3 and 3 restricted schedule. In this schedule, T1 and T2 execute over the interval 0, 1. T1 and T3 execute over the interval closed 1 and open 2. And T2 and T3 execute over the interval closed 2 and open 3. So over the interval closed 0 and open 3, each task receives 2 units of processor time. We now prove that the task system B is only feasible under the 3 and 3 restricted class. The a 2 and 1 restricted schedule, which is also 2 and 2 and 2 and 3 restricted for task system C. It is easy to see from the table 30.3 that several of the scheduling classes are incomparable. As we can see, there are 2 relations that are still open. It is also not known at this time whether 2 and 2 is proper subset of 3 and 2. In this section, we discuss the feasibility analysis and online scheduling of periodic task systems. We will use the following notation. Tau equal to the set of T1, T2 till Tn denotes the system of periodic tasks to be scheduled on M processors. Let Ut equal to Te over Tp, where Te denotes T's execution requirement and Tp denotes its period. Also, let U tau equal to the summation of Ut, while T belongs to tau. And X and Y restricted feasibility test accepts as input the specifications of tau and M and determines whether some X and Y restricted algorithm can successfully schedule tau upon the M processors. For several of the classes identified in the table 30.1, exact feasibility analysis is provable, intractable. A transformation from the 3 partition problem can be used to show that feasibility analysis is NP hard in the strong case. And we can see the theorem 30.4 here. A periodic task system tau can be scheduled upon M processors using some 3 and 3 restricted algorithm, if and only if the U tau is less or equal than M. The 3 and 3 restricted scheduling algorithms have been the subject of several papers. The current state of the art concerning the 3 and 3 restricted scheduling is as follows. There is no schedulability penalty, like theorem 30.4, and efficient runtime implementations are known, but the number of preemptions and inter-processors migrations may be high. Under the partitioning, each task is assigned to a processor on which it will exclusively execute. Finding an optimal assignment of tasks to processors is equivalent to a bin packing problem, which is known to be the NP hard in the strong sense. Several polynomial time heuristics have been proposed for solving this problem. Examples include first fit and best fit. In the first fit, each task is assigned to the first processor that can accept it. In the best fit, each task is assigned to a processor that can accept the task and will have minimal remaining spare capacity after its addition. The worst case achievable utilization on M processors is only M plus 1 over 2, even when an optimal uniprocessor scheduling algorithm, such as EDF, is used. In other words, there exist task systems with utilization slightly greater than M plus 1 divided by 2 that cannot be correctly scheduled by any partitioning approach. Theorem 30.5, no partition-based scheduling algorithm can successfully schedule all task systems tau with u tau less or equal than b on m processors, where b greater than m plus 1 over 2. The theorem 30.6 shows if u tau less or equal than beta b plus 1 divided by beta b plus 1, where beta is the 4 of 1 over alpha, and alpha satisfies alpha greater or equal than ut for all t belongs to tau. Then tau is feasible on m processors under the 2 and 1 restricted class. Here's also the theorem 30.7. The square root of 2 minus 1 times m less or equal than urm ff less or equal than m plus 1 over 1 plus 2 to the power of 1 over m plus 1. The task system in which the total utilization does not exceed square root of 2 minus 1 times m are schedulable using RMFF. This value is significantly small. RM is still popular because of its simplicity and predictability under overload. However, there's one disadvantage of these heuristics is that they can lead to unacceptable overhead when used online due to the sorting overhead. When scheduling online, the best fit and the first fit are preferred. By the previous theorem 30.5, we have the following. Theorem 30.8, unless x equal to 3 and y equal to 3, no x and y restricted algorithm can successfully schedule all task systems tau with u tau less or equal than b on m processors, where b greater than m plus 1 over 2. Now we present some results involving the other classes of scheduling algorithms, the 2 and 3 restricted algorithms. The EDF is a 2 and 3 restricted scheduling algorithm. Although the EDF is a very popular algorithm in uniprocessor real-time systems, but the studies have suggested that it tends to miss many deadlines in the multiprocessor case. In the new algorithm, tasks that have utilizations at least m over 2m minus 1 are statically assigned the highest priority in the system, while the remaining tasks are prioritized on an EDF basis. Thus, we have the following theorem. The theorem 30.9, a task system tau is feasible under the 2 and 3 restricted class if u tau less or equal than m to the power of 2 over 2m minus 1. For 1 and 3 restricted algorithms, based upon the RM rather than EDF, tasks that have utilizations at least m over 3m minus 2 are statically assigned the highest priority in the system, while the remaining tasks are prioritized on a RM basis. Hence, we have the following theorem, 30.10. A task system tau is feasible under the 1 and 3 restricted class if u tau less or equal than power of n over 3m minus 2. It can be shown that if task periods are harmonic, then the schedule produced by RM is a valid EDF schedule. Therefore, we obtain the theorem 30.11 as a task system tau in which all task periods are harmonic is feasible under the 1 and 3 restricted class if u tau less than or equal to m to the power of 2 over 2m minus 1. 2 and 2 restricted algorithms. These algorithms associated a fixed priority with each job and restrict each job to execute exclusively on a single processor. However, different jobs of the same task may execute upon different processors. Such algorithms are particularly appropriate for scheduling task systems in which each job has a considerable amount of state. but not much state is carried over from one job to the next. Hence, we have the following result. The theorem 30.12, if u tau less than or equal to m minus alpha times n minus 1, where alpha satisfies alpha greater than or equal to ut for all t belongs to tau, then tau is feasible on M processors under the 2 and 2 restricted class. The results in the section are summarized in the table as shown in the table 30.4. The exact utilization bound for 3 and 3 restricted algorithms follows from theorem 30.4. The bounds on worst case achievable utilization for partition algorithms follow from theorems 30.5 to 30.7. The upper bounds for the rest of the classes follow from theorem 30.8. The lower bounds on the worst case achievable utilization for 1 and 3, 2 and 3, and 2 and 2 restricted algorithms follow from the theorems 30.10, 30.9, and 30.12. So far, we learned a lot about chapter 30, and here's a quick summary. We had the introduction and classification of scheduling approaches on multiple processors, taxonomy of scheduling algorithms, schedulability relationships, algorithm design and feasibility analysis, partition approaches, and also have a few examples. Thank you so very much, everybody, for watching our entire presentation. If you have any questions or comments, please leave it on the discussion boards and we will answer it as soon as we can. Again, thank you so much, everybody. Have a great day.